Hello everybody. So now let us continue our discussion. So in the previous lecture we were looking at the existence of polymorphism in different compounds, and we looked at an anti-implantation agent, and we looked at the existence of dimorphs. For example, we looked at the plate form and the block form, and we also looked at the differences in conformation, which also manifest themselves further in terms of different intermolecular interactions in the crystal packing. Now we will take another interesting case study. We will be looking at concomitant polymorphism in a fluorinated benzamide. So we have made these benzamides where we have a CF3 and fluoro substituted moieties on the carbonyl side as well as on the amide side, the NH side, and one such specific molecule which has got a CF3, here and a fluoro in the para position on the NH side exhibits this concomitant polymorphism. Now what is important to realize is that polymorphism is a very important phenomena, a very subtle phenomena, which is governed by formation of different crystalline forms which are very sensitive to the crystallization conditions. For example, when we have taken this particular compound, the code is given as A. When it is crystallized from DCM and hexane at low temperature, you can see it crystallizes in the form of blocks. So we call this as blocks, and we refer to this form as A2 form. And when we actually do it, another combination of polar like chloroform and hexane nonpolar solvent at low temperature, we again get these blocks. So you see that the block conditions are obtained under low temperature conditions in a combination of polar and nonpolar solvents. Now when we change the solvent to benzene, which is completely nonpolar at low temperature, we again see that we get the blocks, that is the A2 form. But now when we heat this solution in benzene to room temperature, then we see concomitance observed on slight warming. So we get blocks plus thin long plates. So in this particular figure, you will be able to see that there are some blocks and then there are some thin long plates as well. So you get this kind of two distinct morphologies. The plate form is referred to as A1 and the block form is referred to as A2. And then in benzene, after heating for some time and then cooling and crystallized from room temperature, again you get plates. Okay. So now initially when you have slightly warmed up the solution in benzene at from room temperature, you get both the morphologies. But now if you continue heating for some more time and then cool it, then what crystallizes out is the plate form. Plate form is, that means there is only the plate form now which is present. So there is conversion from the block form to the plate form. And then when you crystallize it from toluene, it is crystallized at room temperature. Again you see concomitance on slight warming and both forms are present, as you can see in this particular crystallization vial. So this is the phenomena concomitant polymorphism, where different polymers crystallize under identical crystallization conditions. And so what was observed is that the block form converts into the needle form on warming, and to see whether this behavior is actually relevant in this particular system, we now performed a series of thermal characterization using different techniques. For example, we started with DSC and then we also followed it up with HSM. So now we have got the pure synthesized compound. So we have recorded the bulk that is called the A bulk, on which we have recorded the DSC spectra. As a function of temperature, you see that in the DSC trace, the compound, first there is a peak at 108 degrees centigrade and then there is a tiny peak at 113 degrees centigrade. So it indicates that there are, in the bulk phase, there are two polymorphs, one melting at 108 degree and the other melting at 113 degree. And the area under the peak indicates the relative abundance of these two forms. That means block is more present and compared to that of plates. Now we do the crystallization experiments and now we separate out the plate morphology. So in the plate morphology, when we do the DSC experiments, in the first heating cycle you see that it melts at 112 degrees centigrade and then you cool. When you cool, you see that there is no recrystallization happening because of the thermal arrest. There is a hysteresis, the super cold liquid does not immediately crystallize. but after a certain period of time, during the process of the second heating cycle, you see when the second heating cycle begins, there is an exothermic peak which indicates recrystallization of a form which melts at 95 degrees centigrade. So, the recrystallization happens during the process of the second heating cycle in the same pan, DSC pan, and that form which is recrystallized is another metastable form which is not the plate form and which melts at a much lower temperature, that is 95 degrees centigrade. Along the same lines, we took the block form, and the block form we did the experiment, DSC experiment in the first heating cycle. Now, this was done at 3 degrees centigrade per minute. We maintained the same scan rate, and we observed that there is first a endotherm at 108 degrees centigrade, followed by another endotherm at 112 degrees centigrade. So, this indicates that there is a possible phase transition at 108 degrees centigrade, which then converts into a new phase which melts at 112. Now, we know that the plate form melts at 112. So, the chances are that the block form converts into the melt form, converts into the plate form, and then it melts at 112. And once it has melted and you cool the pan, there is no recrystallization, and during the second heating cycle, you again see that the process of recrystallization takes place, followed by melting of the metastable phase again at 95 degrees centigrade. So, whether you start from the plate form or the block form, it converts into the plate melts, and it converts into a metastable phase. Now, because there are two peaks here, we wanted to see the dependence of these peaks on the scan rate, because we see that there is a phase transition and then there is a melting of the new phase. So, we now did the experiment at different scan rates. We did it at 1 degree centigrade, 3 degrees centigrade, which is already represented, and then we did it at 5 degrees centigrade and then 10 degrees centigrade. And we clearly see that when you do it at a faster scan rate, then you only see the melting correspond to 107 degrees centigrade. That means it is only the melting of the block form which takes place. However, when you do it at a slow scan rate, then there is a phase transition followed by melting of the needle form. So, the process of melting of the the plate form takes place when you have slow scan rates. So, keeping all these things in mind, the fact that you have got a phase transition followed by melting of the new phase, and you can actually overcome, or you can actually need not have that phase transition when you do it at a faster scan rate, which corresponds to the melting of the block form. Now, you can see these things very clearly in the hot stage microscope. When you start with the plate form and do it at a much lower scan rate, you will see that the plates melt at the characteristic 113.7 degrees centigrade, which corresponds to the melting point of plate. Now, when you start with the block form, this is the first heating cycle. At around 108, you see that these crystals start getting opaque. They are transparent here. Now, they start getting opaque, and then you see there is slight formation of there is a growth of a new phase here at the expense of the block phase, and this is essentially the new plate phase which is being formed. And now you see that it has got converted, it has completely converted into the plate phase, and then it melts at around 112. So that we continue the temperature, it has completely melted at 113. Now, when you cool it and then you perform the second heating cycle, you see that it has solidified, and this new phase, which is the metastable phase, melts at 95 degrees centigrade. And when you continue this process for the third heating cooling cycle, again it has melted and converted into this metastable phase, which again melts at 94 degrees centigrade. So, the metastable state, once it is formed, stays for a considerable period of time, but it essentially originates from the phase transition of the block to the plate form, the melting of the plate form, followed by the conversion into the metastable state. So, you can see that these kind of interesting events can take place, where you can determine the melting points of the different phases from DSC and supported by HSM studies as well. So, this is to tell you that DSC, HSM and morphological experiments give us very invaluable information about the formation of polymers and their interconversion, their stability, and so on and so forth. So, with this in background in mind, let us now go on to the next topic of discussion. We will now talk about another interesting phenomena in the field of solid state chemistry of organic molecules, and we call this as cocrystallization. So, in case of co-crystallization, these are also referred to as multi-component crystals, where we have got to start with at least two components in a certain stoichiometric ratio, say AMBN, which is formed from A and B in a certain stoichiometric ratio, and the properties of this new phase is different from A and B. And to start with, A is a solid, B is also a solid, and the new phase formed is also a solid, which we refer to as a co-crystal. And the formation of the co-crystal and the driving force for the formation of co-crystals originates from both the enthalpic and entropic term. From the enthalpic term, we understand that the intermolecular interactions between the A and B components is greater than the strength of the intermolecular interactions between AA or BB. So, AA and BB have a certain stability, but the nature of interactions between A and B is more favorable and more stabilizing compared to that of the starting material, and that is what enthalpically drives the formation of co-crystals. And there also is an entropic gain, which is coming from the entropy of mixing, which originates when we have the mixing of two reactants of similar size, shape and chemical nature. So, when we have two reactants which have got similar size, shape and chemical nature, and we mix them in a certain ratio, then the resulting phase formed is the formation of the resulting phase is driven by the entropy of mixing as well. And co-crystals have got a definite composition. They can exist in defined stoichiometric ratios, for example 1:1, 1:2, 3:1, 2:1, etc. And it is also important to note that now we are expanding the solid state diversity of these compounds. So, when we have got A solid plus B solid, we are forming, say, AB solid. This is referred to as a co-crystal phase. But when we are doing these experiments of preparation of co-crystals, there is a possibility that you can also end up with polymers of A or B. You can also get co-crystal polymers of AB. Then there is also a possibility that once you have prepared the AB solid, you want to recrystallize it, and that is the time when you can have solvates of AB. You can also have solvates of A and B separately. So, this expands the solid state diversity domain of AB with respect to A or B. At the same time, if A is an acid component and B is a basic component, say for example A is a solid and B is a liquid, then it can form a new phase, AB phase, in a certain stoichiometric ratio, where the acid has released the proton, becomes A minus, and the base has accepted the proton and becomes the conjugate acid of the base, and then there is strong electrostatic interactions which forms the salt. So, this is a salt co-crystal essentially the stabilizing entities here are the salt. You have A minus, a compound, and this acid compound can also be a drug molecule which has got ionizable protons. The protons are lost to the base takes up the protons, and there is a complete proton transfer from the acid part to the basic part. And now these are the constituent species are ions or molecular ions, and then they interact with each other electrostatically to form the co-crystal salt. And along the same lines, we can also have polymers of these salts via rearrangement of different synthons, which can give you the packing polymorphism in case of these salts. We can also have the solvates of these co-crystals. We can have hydrates, or we can have other solvents also included with these co-crystals, and we can also have salts of B only, assuming that B is basic and we add a polar solvent from where it can take up a proton. For example, if you add it in HCl, then the base B will take up the proton from HCl, form the conjugate acid, that is B plus H, and the chloride will be the counterand which will form a hydrochloride salt of the basic compound. So you can also have basic drugs. You need not always have acidic drugs. You can also have basic drugs, for example, which can be a part of the co-crystal formulation, and we can now have the corresponding salt, hydrochloride salt of that basic component, and which can also form solvates along with, and which can also form solvates of salt. So this can form salts of B, and then the salts of B can also form solvates of B salt. So on one side you have got the different salt components, the different forms of salt compared to the starting materials, and here you have got the co-crystals. So this very interesting diversity exists when you want to make co-crystals. Now how do you make co-crystals? Co-crystals are prepared by the technique of mechanochemical grinding. Using a mortar and using a pestle. So a mortar and a pestle is used where you take the starting materials A and B, and then mechaноchemically grind these components A and B. Then the resulting solid which is obtained, you record the powder XRD diffraction pattern, and the powder XRD diffraction pattern for the obtained phase, if it's a new co-crystal phase, will be very different from the powder XRD diffraction pattern of the starting components. Now when you do this mixing in the absence of any solvent, it is called dry grinding. But sometimes to assist the process of diffusion and more homogeneous mixing of the reactants, we also add few drops of a polar solvent. For example, we can add methanol, and then we do something called a liquid assisted grinding. And then this liquid assisted grinding, once we do it for a period of say 1 to 1.5 hours on an average, and then you can again record the powder XRD diffraction pattern of your co-crystallized solid, and you can do the phase analysis in the similar way like you do for the polymers, which we discussed in the previous lecture. And once you have confirmed the formation of the pure phase, to start with there will be some impurities corresponding to the starting materials as well. Now you can take this mechanochemically grinded solid and put it for crystallization. Put for crystallization, and you will then be able to get crystals of different morphologies. And now you can utilize these crystals to do single crystal X-ray diffraction experiments, from where you will be able to get the atomic connectivity of your co-crystal. So again here, similar to that of polymers, single crystal XRD plays a very important role to determine the atomic connectivity and the composition of the obtained co-crystal phase. Now, it is very important to realize that co-crystal contains neutral components. It contains neutral components A, B forming the solid, whereas the salt contains ionic species. So, you have A minus, BH plus, and there is a very strong hydrogen bond. There is a strong hydrogen bond between B and A minus, and depending upon how strongly the base abstracts the proton, there can be a transfer of this proton from A to B. And this, so to start with, hydrogen can be associated with the acid part. This is called a co-crystal, and then it starts getting dissociated. So there is an intermediate position where there is a substantial lengthening. So this is say L1, this is L2. L1 is much less than L2, but here L1 is nearly equal to L2. And finally, when the proton is transferred to the base, then L1 is greater than L2. So this is a very interesting phenomena which is observed in the solid state, because depending upon the position of the proton, we can say whether it is a co-crystal or whether it is a salt, and there is an intermediate phase as well, where the hydrogen atom is positioned symmetrically between, or almost near symmetrically between, the two acceptors, and this phenomena is referred to as the salt co-crystal continuum. Okay, and it is only by a very careful structural characterization of these co-crystals and the treatment of the hydrogens, we will be able to unambiguously establish whether it exists as a co-crystal or whether it exists as a salt. In most of the cases, if you have good diffraction data, you will be able to locate the hydrogen atoms very cleanly, and you will be able to confidently say whether it exists as a salt or it is in the intermediate phase or it is the pure co-crystal phase. And therefore, the salts are characterized by high lattice energies. These are characterized by high lattice energies in comparison to that of the neutral compounds. Now, just like synthons play an important role in solid state, in cocrystals also it is the synthon arrangement, it is the synthon strength and the arrangement of the different synthons in the crystal packing which originate because of the interactions, the heteromeric interactions between the A and the B entities, which contain the functional groups that engage in synthon formation, which gives rise to the co-crystal. So, for example, if you have hydrogen bonded co-crystals, we can have the well-known dimer. This is the acid dimer which we have all studied. So, this is the homodimer. This is a homosynthon. Along the same lines, we can have another. So, this is the homodimer or a homosynthon involving the acid, and this is involving the amide homodimer. And similarly, we can have an acid amide homodimer as well. So, this is the NHO and this is the OHO, and this is a hetero dimer involving the acid and the amide. So, these kind of heterosynthons are also present in case of the different co-crystals which are formed by the interaction between the acid and the basic functionality. So, the carboxylic acid is the acid component, amide is a basic component, the NH part, okay, and this can interact with each other. We also can have cases where the acid can interact with any nitrogen containing species. So, you can have, for example, pyridine, and pyridine can form OH and hydrogen bond. So, the OHN and synthon becomes extremely important, and there are large number of co-crystals which contain this OHN hydrogen bonded synthon, this coming from the acid part, and this is the basic part. Along the same lines, you can also have other nitrogen containing species. For example, we can have this particular base which contains the lone pair. We can have two nitrogen atoms, both basic in nature. They can engage in hydrogen bond formation, and this can engage in hydrogen bond formation. And we can also have other cases as well, where we can have oxygen as well, NH. So, we can have different kinds of functionality which form these kind of heterosynthons involving interaction between an acidic component and a basic component, and these are considered to be the primary synthons or the basic building blocks which are present in co-crystal systems. We can also consider even more extended structures now, where we can consider, for example, 3-amino phenols plus bipyridines. So, here we can see, for example, NH, N, OH, this is N, we have OH hydrogen bond, so we have OH and hydrogen bond here, we have a NH and hydrogen bond here, and this can now extend further. Okay. So, again we can have here the NHN and we will have here the NHO. So, we can have these kind of hexameric motifs 1, 2, 3, 4, 5, 6, and we have this kind, this can extend further now, and therefore we have the ladder like arrangement. We have the ladder like arrangement which is present. So, these are some of the fundamental building blocks in case of co-crystals. Now, what is more important in co-crystals is why this field became very popular, exciting, and application oriented is because it gave birth to the discovery of pharmaceutical co-crystals which are of relevance in the drug industry. So, the drug industry is always interested to make drugs which have got improved performance, particularly in terms of the solubility and the permeability of the drug. So, the solubility and permeability plays an important role, and it is also important that when you formulate a drug, it converts to the famous ADMET rule, where A stands for adsorption, D stands for digestion, M stands for metabolism, E stands for elimination, and T stands for toxicity. And this is what constitutes the pharmacokinetic profile, the pharmacokinetic profile of the drug, which we call as PK. So, these pharmacokinetic profiles of the drug becomes extremely significant. Now, there are two reasons why this concept of pharmaceutical co-crystals become very important. One is to enhance the chemical properties of the drug, that is we can either get salts which are going to be more soluble compared to that of the parent drug which have poor solubility, and we can also improve the physical properties of these drugs, because when you make drugs there are a lot of practical issues associated with drug formulation. For example, the shelf life of the drug, the stability of the drug, the hygroscopicity of the drug, and the mechanical processing of the drug, that is the tabletability of the drug, the powder characteristics of the drug. So, some of these properties play a very important role in drug processing as well, and it has been observed that co-crystal formation plays a very important role in overcoming some of these limitations with respect to the properties of the drug. For example, norfloxacin with isonicotinamide ofloxacin with difenic acid, and itraconazole with succinic acid. These improve the solubility of drugs. In the sense that they exhibit greater solubility compared to that of the parent drug. And because there are also problems related to taking up uptake of water by the drug, and that is not a very favorable thing, particularly if there is atmospheric moisture, then there is a problem of formulation of the drug, packaging of the drug, and also the storage of the drug. So, in this regard, caffeine is very sensitive to moisture, and there are problems associated with storage, and because it is susceptible to hydration with change in the atmospheric conditions or the humidity conditions outside. And this caffeine is now stabilized by forming a co-crystal with oxalic acid. So, this co-crystal which is obtained has got is now having a better shelf life, and it is sufficiently stable for several weeks. Similarly, we have a very common drug called paracetamol, which has got poor compaction properties, which we called as tabletability, and we now make a co-crystal of paracetamol with oxalic acid, and this co-crystal has got better tabletability. So, you are able to make a nice tablet of this drug if you have the co-crystal form, whereas this pelleting of the drug when it takes place is more compaction is better, and the drug quality and the pill quality is also better because of the nice flow characteristics. So, paracetamol per se has got poor compaction properties. The tablet which is formed is not very uniform and stable, whereas it has got better tabletability with oxalic acid. So, keeping in mind some of these most important applications of pharmaceutical co-crystals and keeping in mind that they enhance the solubility profiles, we will now look at pharmaceutical co-crystals in more detail and in terms of different applications and the mechanism of its action in case of drugs. Thank you.